equals that k radical 2 over x naught times I. Okay? And you can check that indeed when t is equal to 0, x equals x naught. Let's see. When x equals x naught, that goes out. You get x naught, arc cosine of 1, which is 0. Yes, at t equal to 0, x equals x naught. Now, one thing you can, now, again, if you had numerical data for k and x naught, you could plot this using software in MATLAB, right? And you'd get, well, the way it is now, t is given as a function of x, but you easily can get, all you need in MATLAB is t points and x points. You can draw the graph any way that you want. Now, one thing which is interesting is, though, is that even though we don't have the explicit solution for x as a function of t, I can tell you from this equation at what time it'll hit the origin. Okay? So, particle reaches origin when x is equal to 0, right? Right? Plug in x equal to 0 and see what happens over here. On the left, I find this goes to 0 and x equals 0. I get x0. Arc cosine of 0 is pi over 2. Okay? That equals k, the square root of t over x naught. Let's just call that t final. Okay? So just, you can solve for t final, obviously. So it tells you, exactly, at what time it'll reach the origin. Okay. Again, an example of a nonlinear equation. Okay. Okay, now, let me at least, I don't know how far we're going to get on this one. This is the most interesting problem we've done so far, the one coming up. And let me explain to you again what I'm going to do over here. Okay? It's very common to use this approximation that, gravitational field, there is mg. And that's good if you're basically working near the surface of the Earth. Okay? We launch spacecraft, okay, and if indeed the gravitational force was always mg, it would always come back to the Earth. It would never get what's called escape velocity. So what we want to do, now that we know how to solve or integrate certain types of nonlinear equations, let's look at these two. We're going to basically do the same problem in parallel. One's using a uniform gravitational field, and next time using inverse square field, and we'll compare the two graphically. Okay. So here's the situation. Okay, here's our spherical Earth. Too bad. Here's the center of the Earth, call that O, okay? And then I'm going to just introduce a set of axes, and again, we can just do motion along one direction, the y-axis, okay? And notice I just, for simplicity, I don't take y equal to 0 to be on the surface of the Earth, I do it from the center of the Earth. It just makes the mathematics easier, right? If you wanted the altitude, clearly just subtract the Earth radius from that, okay? So, and here's the situation. At t is equal to 0, I've got a particle over here, okay? And t equal to 0, y equals the radius of the Earth, so it's basically y equals big R, and y dot equals v0, which is positive. Okay. So what's happening basically at time 0, I got a particle, let's say, which is on the surface of the Earth, okay, over there. I just drew it this way. Obviously it doesn't make if I drew it that way anyway. Okay, just that people seem to like gravity up and down. Okay, but it's really spherical, so it's symmetric. Okay. So t equals 0, the particle, let's say, is at y. R is the radius of the Earth. Let me just put that down over here. So that distance is r. R is the Earth radius. So t equal to 0, it's basically on the surface of the Earth, and I throw it up with a velocity v0 positive. Okay? What's going to happen? Okay? Well, climb and climb and climb and climb. If it's a uniform gravity field, right? Stop instantaneously and then come back to the Earth, right? Inverse square fields will be completely different. They're a little bit counterintuitive, but you'll see what's going to happen with the inverse square field is that there's a parameter called the critical velocity. If you don't give it enough of an initial velocity, it will do the same thing qualitatively as this uniform gravity field. It'll go up and up and up, but of course, what's going to happen? Now that we're considering the inverse square field, rather than just the uniform mg, it's going to climb higher than the one that had the uniform gravity field, but it'll eventually come down again. However, there's a certain critical velocity v0 that you need where it will go up and up and up and never return. That's called the escape velocity. And that's why we can launch rockets to Jupiter and stuff like that, okay? So what we want to do is compare the two and actually put numbers in and look at plots. It'll be, I think, very interesting and informative. Okay, so let's do a uniform gravitational field first. Okay, I have these class evaluations, so at 20 of, I really have to stop and I can give those out, okay? So when it's 20 of, so when we stop.
20 of what?
The class goes till 1:45.
So
1:40, yeah.
15 minutes.
Yeah, in 15 minutes. Uniform gravitational field. Again, this is not in the book, but you know. Okay, we all know that, right? It's Newton's law. Second y with respect to time is equal to minus rho g. That's it. The famous 32 feet per second squared, right? That's the acceleration in the surface of the Earth. Okay, and you integrate that subject to the initial conditions. Okay, you should be able to fill in the blanks. You're going to get r plus v0t minus 1/2 gt squared. You've probably done this, you know, in your physics courses. Okay, and again, what you do, you integrate once, you get y dot is minus gt plus a constant. But t equal to 0, you know it's v0. Integrate again, and get the other arbitrary constant because at t equal to 0, y is equal to r. So that's the solution of that differential equation subject to those initial conditions. Okay. And let's just make little notes over here. The maximum y is equal to, it's easy, what you do basically to get max y is that dy dt equal to 0. They'll give you the time, and then given that time, you plug it in. I assume you can do all this thing. Max y is r plus v0 squared over 2g, and it occurs at t equals v0 over g. That's when the thing reaches its maximum height. Okay. And then particle returns to Earth, right? It's symmetric, right? At t equals just twice that value, right? Symmetric, 2v0 over g. Okay, and that's basically the uniform gravity field. Okay, let me go to a different part of the board over here and do the inverse square field. This one from scratch. Okay. Okay, we have, again, F equals ma, the mass times the acceleration, equals, you know, it's a minus, right, because it's in the gravity field, so the particle goes down over here. But now, it's not just now it's not mg, it's the inverse square field, okay. I'm going to state in words what you should remember from your physics courses, right, that any two particles attract each other with a force that's proportional to the product of the masses and inversely as the distance. So the magnitude of the attractive force is the gravitational constant. What is that, something like 6.67 10 to the minus 11th in MKS? You can look it up. That's the gravitational constant for the Earth, okay? Times the mass of the Earth, times the mass of the particle, divided by the square of the distance between their centers, y squared. That's why I put y equal to 0 over there. That's just Newton's law of universal gravitation. Okay? So, we have the second derivative of y with respect to time equals minus cap g me over y squared. Again, where me is the mass of the Earth. Okay, now I want to get this little g in here, and this is actually a way of defining it. You know, when people say at the surface of the Earth, you know, the little g is 32 feet per second squared, how the heck did they get that? And let's assume that, you know, you can measure it, but let's do it analytically, okay? What happens now is this thing has to be consistent, right? Let's put a particle right on the surface of the Earth and calculate the force of attraction based upon Newton's law of universal gravitation, okay? So for particle, at y equal to r, what does that mean? For particles that are just sitting on the surface of the Earth, right? Newton's law of universal gravitation says that the attractive force has a magnitude, gravitational constant, mass of the Earth, mass of the particle, over the square of the distance, which is now r squared. Right? That's, right? Newton's third law of universal gravitation. But what we also say is that what? In the engineering practice, when things are near the surface of the Earth, everyone says that the force is equal to little mg, right? Little mg. Okay? And therefore, you can cancel the m's, and then you get this expression for little g. Gravitational constant, mass of the Earth of r squared. And believe me, if you basically just look up the value of cap g, let's say in English units, the mass of the Earth is available, the radius of the Earth is available. That's how you get 32 feet per second squared, or 9.8 meters per second MKS. That's where it comes from. Okay, a lot of people don't even know. They say, oh, it's just mg. They don't even were taught, where does little g come from? And that's basically, you know, the story over there. Okay, so what's going to happen now is that I'm going to basically use this to get the GME and plug it over there. So gravitational constant mass of the Earth is nothing more than little gr squared. Okay? So now I will then get the second derivative of y with respect to time is equal to, minus r squared g divided by y squared. Okay? All I did was plug in for GME gr squared. So that's our equation of motion. Okay? And again, I've introduced little g just to make a comparison with that. But, you know, there's a rigorous definition of little g right over there. So, the equation of motion when it was a uniform gravitational field was what? Y double dot equals minus little g. Now, look what it is. It's minus little g squared the radius of the Earth divided by y squared. So, as it gains altitude, the acceleration diminishes. Well, over there, it always has the same acceleration, or deceleration, right? Talking about. Okay. Let's integrate this equation now. Okay. This is a second order nonlinear equation, but the independent, remember I said in mechanics always happens, the independent variable is missing. So you say, let dy dt equal the speed, and then y double dot, which is v dt, is equal to v dy dy dt, v dv dy. Okay? And we've done this already in the last problem. I'm not going to redo the algebra of the integration. What will happen is you'll get the following. You'll find that v squared of t, square the speed, is equal to the initial velocity squared minus 2rg plus 2r squared g divided by y. Okay? You know how to do that, right? You integrate this thing and you have the two initial conditions. At t equal to 0, y equals big R, and y dot is v0. So you can integrate, and again, that's conservation of energy. Okay? Now, we have the concept of escape velocity. Let's check this. V0 squared minus 2rg plus 2r squared g over y. Okay. So, just think about this physically. You've got this particle over here, t equal to 0, and you eject it with a very high speed, v0, you know, radially away from the Earth. Okay. What's going to happen now is that if I reach what's called escape velocity, the idea is that y will just keep increasing and increasing, and the velocity will be diminished, approaching 0 asymptotically. So, to escape, this is what's called escape, to escape Earth's gravitational field, choose v0 such that what? as y approaches infinity, it just keeps going up and up and up, the speed goes to 0, okay? We know it has to diminish, right, even though it's inverse square field, right? But the difference here is that in the uniform gravitational field, it will always, no matter how big V0 is, it's always going to come back. You can see over here, right? There's no way that it can keep on going, right? Just look at the mathematics. It's going to reach a certain altitude, a higher altitude depending upon, you know, how big V0 is, but it always comes back to the surface of the Earth. But because of the nature of this equation, we can actually show that we can get a solution where y goes to infinity as the speed goes to 0. So let's just plug that in. So speed is going to 0 as t goes to infinity. So I got V0 squared minus 2rg, and that goes to 0, right? So if I solve, I find that V0 squared equals 2rg. And this is what's so-called the escape velocity. We call that VE, is the square root of 2rg. That's a critical number. So if you take a particle and release it with initial speed of VE from the surface of the Earth, it will never return. It just keeps going and going. Any initial speed V0 less than VE, it will return. Okay? So V0 greater than VE, that means that y will go to infinity. If you give it an initial speed V0 less than VE, that means particle returns to Earth. It returns to the Earth. Okay. I think we have to stop now. Yeah, okay. So we're going to pick this up on Monday, and we're almost finished actually with the analytics, and then we're going to see interesting plots. I'm going to show you, you know, oh, here's a case where V0 is less than VE. Even then, there'll be a difference between the two, right? Because the uniform gravity field will come up and come down. This guy will also come up and come down, but you'll see that it reaches a much higher altitude and it takes much longer to return to the surface of the Earth. Okay. So let me just give this out. Okay, first I need a volunteer. You know, I'm supposed to be official. I'm going to leave the room, and I need a volunteer to just take it to the ME office. Anybody?
Where's the, which in the office on the fourth?
I think on the fourth floor, okay?